So, good afternoon, everyone. It's again my turn, but it's a pleasure because I have the privilege to introduce to you the awardee of the third edition of the ESMEC Alumni Award. This was an award which has been created by the scientific committee of the school, by the director, and ESMEC is very proud of this award, so it's something we care a lot about, and you can understand why. Because as I said during the round table, we want to inspire you, okay? We want to inspire you so that you can stay in the field and progress the field. So basically, my message is always the same one that I made a couple of days ago. So that's why I'm so happy. I'm so touched even to give this award because after selection, and I want to point out that the selection has been done by an international committee, completely external to the school, and the committee unanimously has considered to award the third ESMEC Alumni Award to Dr. Marco De Vivo. So please join me to recognize Dr. De Vivo for this, for us at least, a very special award, okay? And now, before giving the floor to Marco, he will give you a kind of inspirational lecture again, and I want to present Dr. De Vivo to you. Maybe some of you know already him, but Dr. De Vivo graduated in chemistry from the University of Bologna, and that's why I'm so proud, because even the PhD, I was not in the committee, so even the PhD was awarded by the University of Bologna, and so Marco shifted from a pure chemistry curriculum to a PhD in, at that time it was called in pharmaceutical sciences. So that's why he was in Urbino, and he participated, like all of you today, to the Urbino school. And what I would like to emphasize, because you will see the CV is impressive, but what I would like to emphasize is that maybe you can take as a take-home message, okay? First, never be focused on a particular field, because he was first studying chemistry, then he switched to medicinal chemistry, and then he had a long-standing experience abroad, because he was in the US, first as postdoc, and then working in a company in the US for 5 years. Then he came back to Italy, to the IIT, where he's working at the moment, and specifically he's the head of the molecular modeling and drug discovery laboratory. And he's also the director of the Italian, I don't know if this should be pronounced in English, in French, SICAM, okay, SICAM IT Simul node of the SECAM, because SECAM should be French. And yeah, and also something that I appreciate personally a lot, that he also finds the time to work for the community, to give his service to the community, because he's an editor, he's in the editorial advisory board of JCIM and CHEM, two journals that you know. The first one more focused on computational chemistry and modeling, and he's also the executive editor of the Journal of Chemical Theory Computation, always from the SES portfolio. He has received several awards. Maybe you will mention, Marco, those, so I will skip them, I don't know. But in any case, the very last remark I want to make is that he belongs to the board of Divisione of Chimica Farmaceutica, so that's why I'm very, very proud today, and of the same one that was presented by Isabella and, you know, the Divisione of Chimica Farmaceutica, where you belong to. And also, considering the entrepreneurial part of his career, he is also co-founder of Yama Therapeutics, which is focused on neuroscience drug discovery to treat brain disorders, which are, as we know, tremendously unmet medical need. So, Marco, thank you very much. I would prefer to first to listen to the talk, and then to give to you then the award. Oh, as you prefer, director, okay?
Well, first of all, thank you so much for this introduction, for the prize. I'm honored, I'm happy, so happy, although it is touching, you know, to be here after 20 years. So believe it or not, I was one of you 20 years ago, which sounds to me the day before yesterday. To you is a long time. To me it seems time flew away. But it's been incredible. So thank you a lot to all the committee, each member, and let's go with the story I have for you today. And so the story starts with me, because I wanted to share with you my journey a little bit. And as Professor Bolognese, Maria said, I was here and I digged into my folders and I found the poster. So I had to share it with you.
So it's true.
So that's the poster I had, and it was on catalysis. So I was into the study of protein kinases, so always interested in pharmaceutical chemistry, even as a chemist before that. I wanted to do drug design. That's why I always pick problems related to drug design. And for those in computation, this is the negative frequency of the transition state of the reaction, which I still found in the folder, so I wanted to show these. And so you see the reaction happening there. And then what I want to show you is how I went from this to actual drug discovery, I would say, today. So you'll see how you can then start a journey that will lead you wherever you want, wherever you want to go if you push it. And I have to thank my supervisor at that time, Professor Maurizio Recanatini, Professor Paolo Carloni, where I spent a couple of years at that time in Sissa, in Trieste. And here you see a younger researcher, now big professor, Professor Andrea Cavaglio, at that time was also in the group with Maurizio Recanatini. And so this is how I came here. This was the science part, but I also found the fun part. So that's the picture of the social dinner. So take pictures tonight, because in 20 years you may use it. So don't ask who I am, otherwise I get annoyed. So you'll see this is before the PhD and this is after the PhD. So you can see the price of it. And then, since this is Urbino, I have to point out somebody that didn't change at all. But if you wonder, there is a professor here in Urbino, and this is Professor Giovanni Bottegoni, so who was sitting with me at the table that evening. Okay, so as Maria Laura said, after the PhD, I wanted to explore. And if you feel you don't know where you will be, that's totally fine. I'm going to stress this to you because I had no idea what I was going to do after. And that gave me always a sense of frustration, to be honest with you, because I wanted to know what I was going to do. And that was always, on one side, stress, on the other side, motivation. And then I was lucky in a way because I could join the lab of Professor Michael Klein, a pioneer in molecular simulation. So I was really into computation at that time. And I could continue to study pharmaceutical relevant targets from the catalytic point of view, right? I wanted to understand the mechanistic way in which these enzymes work, and these are all enzymes that deal with metal ions, so challenging from also a computational point of view. And this was a tremendous learning experience for me, okay? Not only scientific, which of course it was, but also personal, because you are in your 30s, you live abroad, you are in a group that is international, you challenge yourself. So one of the messages, try always to work in the best lab or the best scientist you can, because the projects will be better, the colleagues will be better, the opportunities will be better, the infrastructure and resources will be better, you will be challenged, and that's how you keep improving yourself. So after this experience, I actually wanted to do drugs, and I was kind of frustrated because this was all pure computation, so I wanted to really make drugs. And so one evening, sitting on the couch, I see there is a position in a startup at Yale. So Yale, I knew that it was cool, but I didn't know exactly where it was, so I had to check. And it was on the line to Boston. I wanted to go to Boston. So I applied because there was this person here who was the leader at that time, and this is a pioneer in computer-aided drug design. So I applied, and I got a job in what was called at that time Ribex Pharmaceuticals, and it was using the structure of the ribosome to do structure-based drug design. Super cool. In fact, in 2009, there was a Nobel given to one of the founders, Thomas Stites. And I could join this incredibly outstanding scientific environment, could join, in a way, the lab of Bill, and I was always intrigued by this review, which is still very timely. So especially the very first lines that I always use and I read with the students when I teach. So you should go back and read this masterpiece, I would say, from Bill Jorgensen on the role of computation in drug discovery. The bottom line, we speed up the process. We prioritize compounds. We don't make drugs on the computer. It's a multidisciplinary work, as you will see. So that's the message. So I could be there for a few more years. And then IIT came along. Actually, it wasn't planned at all. So again, you cannot plan everything. I was planning to stay there longer. But then this opportunity came up. It was a great opportunity. I was scared to come back. My mentor at that time told me when I said, I'm going to go back to Italy, and he told me, think twice before you cross the street. That was the reply from my mentor, okay? So, and I came back, and then I invested on IIT. It was a new institute, and I can say today there was a great choice, okay? I'm very happy to be back in Italy. Not everybody is so lucky in a way to have the opportunity to come back. So I could build my group over time, and I still have a core of computational people in the group, you will see. But then I could add synthetic medicinal chemistry, so we design compounds and we make compounds, and to some extent we can also test the compounds inside the group, at least initially, okay? So to do so, and we always go back to catalysis, because it's at my heart, because I started with catalysis, but then drugs as well. So this is the group today at IIT. It's a big group, and again, people with different backgrounds, from medicinal chemistry again to computational chemistry and biochemistry. What are the topics we have? So you'll see we are very fond of enzymes, again, that deal with nucleacids, the processed nucleacids, RNA and DNA. We work on proteins bound or inserted into the membrane, but also lately, given to excellent collaborators, I found on nanozymes, so nanoparticles capable of catalysis. Now, everything we do appears in terms of simulations. So we want to understand through molecular dynamics, mostly, how they work, and then transform, use this knowledge to actually design small molecules that can modulate, typically inhibit these systems, which are always peak because of their relevance from a pharmaceutical point of view. We synthesize compounds, we test compounds, but then you see we need, of course, to collaborate with experimentalists to test the compounds in vivo for their properties to push the drug discovery. So this is where you create value, guys, because here you can, intellectually it's very rewarding. You may have an impact in the long term, but here you create new compounds. And you see that's important because you create new IP. And new IP is what then you need to attract money from foundations, sometimes, but also from investors. So you need a patent to do that. And you see what I mean by that. So we have been, I want to talk briefly, give you a couple of examples where we go from function to inhibition, from inhibition to drug discovery. So we have been quite active on all these enzymes that deal with nucleacids. So polymerases, they extended the DNA or RNA. Nucleases, they cut it. ribozymes, these are RNA enzymes, so made only of RNA. Topoisomerases, they control the topology of DNA. They all are metalloenzymes at the very core, because you need always to have the presence of metal ion, which goes back to my PhD, by the way. So I kept that interest in a way. And then we use classical and molecular dynamics or quantum simulations to look at the system in the reactant state, in the product states, and then we are interested in how they move from the reagents to the products, passing through the transition state, and then we retrieve the energy for this process, the mechanistic features, and then you can connect these to experimental data, existing ones, but also generate new ones, or also use this as a template to design compounds. So for example, in this specific case, you'll see here the nucleotide in a polymerase called polymerase eta, a good target for cancer, which is going to be added to the filament here. This is quantum simulation, and so everything you see here is treated at the quantum level. And why we have investigated this particular reaction? Well, because we looked in detail at the existing structural data of all the ternary complexes in the protein data bank. So if you take all the structures that have the enzyme plus the nucleotide plus the substrate, which is a DNA, then you will see that they all conserve a certain intramolecular hydrogen bond, which is used to generate a mechanistic hypothesis, which is very broad, because you have now polymerases from eukaryotes, prokaryotes, viruses. They all conserve this particular interaction, which was there in the existing structural data, but nobody could see it at least until the moment. So we could propose a self-activated mechanism for nucleic acid polymerization catalyzed by DNA and RNase polymerases. Now, in the same way, especially for those of you that are working in computation, you always have to stay close to experimental data. That's how you validate whatever you do through computation. So otherwise, it's tough to convince people that you can be real, okay? These are other examples. Did I do some? Okay. These are, no. This is my computer. Got stuck. Let's see if he wakes up. Yes. Okay, we skipped a few slides. So let me see. Well, anyway, so these are papers where we have looked at other features in other enzymes, like a strategically located arginine lysyl residue, a transient and flexible cation pi interaction. These are all features that are useful for catalysis and that were detected in the structural data. But then I want to show you one case here. This is an enzyme that cuts the last nucleotide of a filament that is growing in case it is wrong. So this is classical MD now, just to show you that we have investigated the role of a third metal ion that is placed in the crystal structure right here, and it's not clear how it is recruited. And there is a conserved aspartic residue here. You see this is coming from the bulk, and then there is the flipping, and then it is placed in that position. Now, just to show you that now this fits the structural data, and then we can explain why that particular residue is conserved, why it is flipped in a certain crystal structure before catalysis and not in the other after the ion is there. And that's how you understand better at the atomistic level how these enzymes work. And that's the impact you can have. Now, from there, I want to show you a case where then we are working, by the way, we have developed compounds against those enzymes, but I have to pick some cases here. So I want to show you this. This is the ribozyme. This is group 2 intron. It's the largest piece of RNA, single piece of RNA simulated so far, to my knowledge in the literature. It's 420 bases. It's not huge, but it's all RNA. And why can we simulate this? Because it's very structured. There are X-ray structure of these RNA pieces, which is quite unique, because usually RNA is very floppy. And we are interested again in the catalytic site where the splicing reaction happens. So the RNA has to be self-cleaved. And there is the 2 magnesium, like in all the other cases, but there are these potassium ions that are always present. Now remember, there are no amino acids here, because this is a structure made of RNA. Ooh. And what we investigated is the so-called toggling state. Now, I can't go into the details, but when they resolved the structure, there was this conformational change of this particular junction called junction 2,3, which from one stage of catalysis to another stage where both crystallized goes through this conformational change. And then the experimentalists, we are collaborating with the laboratory of Marco Marcia at the MBL and Anna Pyle at Yale, could not place this structure along the catalytic cycle. So what we could do is to apply metadynamics, move the system from one minimum to the toggling state, and see what is the trigger. Now, the trigger in our simulations is the release, the spontaneous release of this potassium ion. Once this goes away, then you can have the flip of this junction here. I'm not showing now all the process, but at least you see that the trigger is that this potassium ion has to leave, which is what happens here. And this is actually accelerated or catalyzed if this particular base, which is conserved, is protonated. And we have calculated also, in that case, the role of that protonation. So again, this seems a detail, but it's not, and I'll show you why. And by the way, this is the work of Jacopo, who now is in AstraZeneca. So he was studying a detailed reaction, but then he's actually working on RNA in AstraZeneca. Why? Because the intron is the ancestor of the human spliceosome, which is much bigger, much more complex, and challenging to be crystallized. So the cryo-EM maps were not able to solve at higher resolution the catalytic site till last year. And this is the overlap of the potassium ion now that has been seen in the structures with our model that was published in 2019, where we were giving a role to this particular ion. So just to say that now we are in a position where molecular simulation, can be used for the prospective interpretation of structures, not only a posteriori explanation of facts, which is always possible in a way or the other. And there is this endorses the synergy between computation and experiments to look at these multi-component large systems. So you have DNA, ions, water, and so on. So that was a good example, I think. So what do we do now from here? Now, the spliceosome, the human spliceosome, is a validated target for cancer and neurodegeneration. So we are interested in blocking it in a new way, because now we know that we may target that specific site. So we have all the structures coming from our simulations. We have our internal library of compounds at IIT. So we screen at that particular site the target, and then you see that we got compounds that are indeed bound. So we have crystal structures of our compounds bound at the catalytic site, replacing also the K1, and this is done again in collaboration with experimentalists, and this is just to show you that we use MD in different flavors to look at binding, and if the compound can bind there, can stay there, and prioritize compound for synthesis. So now, where are we here? Well, it's quite exciting, because we have almost 40 co-crystals of compounds bound to this RNA target. We have already synthesized more than 50 compounds. This is new IP, so we have now a new pending patent on these compounds, and the paper is submitted, but not yet with the compounds, I must say, because as you know, first we have to patent the compounds, and then we can publish them. So, but I can show you one of the best compounds we have so far, which is 1.7 micromolar. So it's not as potent as we want, but it's the most potent compound in the literature against this target. So you see how we went from understanding in detail at the atomistic level the reaction to the design of compounds, the synthesis, the testing, and everything. So why this is important? Well, this was mentioned at the beginning in my introduction by Maria Laura, but we want to make compounds to have an impact. In fact, when I started chemistry, my first choice in theory was medicine, but then I changed for some reason. So I wanted to have an impact on patients. So there is a class of compounds that we have developed that has been patented and then has been used to launch Yama Therapeutics. It's in neuroscience. And I want to tell you the story briefly of Yama Therapeutics. But there is another class, for example, of compounds coming from the group. Again, after simulations, design, synthesis, and patent that has been used to launch Alira, which is on cancer. So the message is that you can indeed go from mechanistic insights to real applications. And being in an institute that is called a technology institute, that's what we want, technology transfer. So that's how we do everything in the pipeline. So briefly, I tell you about Gamma Therapeutics. Now this is targeting a transporter in neurons, a transporter that let ions go from the outside of the neuron inside. So we are interested in understanding this cycle here. That's called NKCC1. 1 sodium, 1 potassium, 2 chlorine ions. And it comes out that these particular transporters can work through what is called the alternative gating mechanism, which can have different flavors. Okay, so we have to do MD simulations to understand the mechanism. And this is actually, it has been solved, but then through a collaboration with the crystallographers in US, Erukao, we could get the co-crystal of an FDA drug called bumetanide bound to it. Now, this drug is actually a diuretic, so it acts on an isoform in the kidney. But we are interested in blocking, for reasons that I don't have the time to explain now, these particular targeting neurons, because then you balance the chlorine homeostasis inside the neurons, and this is related to neurological problems, especially neurodevelopmental disorders. So we know now the drug binds in the outer vestibule when the transporter is open on the outside. So again, we can run simulations. This is just to show that we have looked at the stability of the complex in the paper, and then we can do structure-based drug design together with the investigation of the mechanism in which this transporter works. So this is just to show you that this is the simulations of the transporter in the membrane. The balls are the ions outside, inside, and we want to go through this cycle. This is pretty complex, to be honest, to look at, because it's not a channel that there is a pore letting the ions go through, but it has a transport. It has to do like this, basically. So the motion, the degrees of freedom that are involved in this conformational change can be quite complex. So we started to collaborate with Michele Parinello, leader in the field of molecular simulations and enhanced sampling, to look at the motions from the outer vestibule, outward open, inward open. And this is all using a machine learning algorithm that detects the best collective variable to be used to accelerate this transition. I know this is a very heterogeneous audience, so I just want to explain this in simple words. So we are pushing the system to do this conformational change, but we have to push it in the right direction. And since it's complicated, we use machine learning to analyze what are the degrees of freedom that allows us to do this motion. And here you see that the transporter is open. So I don't know if you had the time to look at this, but now it is open. So this is work in progress, and it's how we are phasing now the investigation of this particular target with Manuel, who is doing the PhD with me. So going back to drug design, we have the structure, we know where the drug goes, we can have the computer-aided drug design, the synthesis, the in vitro assays, the DMPK studies, we do virtual screening and docking, but then we do a lot of FEP for those in the field, free energy perturbation, to do lead optimization, and this has been then the core of the pipeline of experiments that was used to build Gamma Therapeutics. When investors decided to invest in the compound that I show you, it was not only for the compound, it was for the platform that we have. So we can go after this particular transporter and other transporter thanks to a collaboration with a neuroscientist I have at IIT. But let me stay for a moment on MedChem, otherwise you see simulations, you don't see compounds. That's the chemical class where there is the lead compound. So when we came up with this chemical class through virtual screening first, ligand-based at the very beginning and structure-based at the end, we could investigate all the anchor points that you see here. So, for example, the sulfonamide substituents, the alkyl chain, the R2 position here, and also the carboxylic acid. This is a CNS drug, so you don't want the carboxylic acid in theory, but also the FDA-approved drug bumetanide has a carboxylic acid. It turns out that it's quite important. And it makes sense if you think about it, because it has to target a transporter that attracts ions, so things that are charged are somehow, liked by the target. So we build a quite extensive SAR. We don't have to look at the compounds. I just want to show you that this is the work at that time of one PhD student. That has in his thesis several compounds that have been made to identify at that time the lead compound, so an extensive structure activity relationship to select the best NKCC1 inhibitor. And that's the story of the project. This is the collaborator I have at IIT, Laura Cancetta, co-founder with me of Yama Therapeutics, Annalisa Savardi, who did the PhD with Laura, but then here in this audience I want to point out Marco Borgogno, who was also a PhD in this particular program, so a PhD. He did the PhD with me. Now he's the head of the MedChem at Yama Therapeutics, and actually the compound, the lead compound, is going into the phase 1 at the end of this year, and that's the compound of his thesis. So it's, I think it's very cool to have a compound going, oh my God, I'm sorry. I'm gonna, a story like this. So I'm very proud of Marco and happy of his career so far. So we went from the first disclosure of the compound and the chemical class to the extended SAR, to the pharmacological characterization, and also the translational science to have the preclinical development. So bottom line now, we have a compound that has been highly characterized for everything you need to do in terms of moving the compounds into the preclinical studies. The preclinical studies are over, and we, as I already anticipated, are expecting to enter into phase 1 clinical trials at the end of this year. So, and we started, just to stress this, from catalysis, at least me. So you can really span this and reach your goal. It took 20 years, but to do everything. But anyway, it's a good time. So this is, I think I used my time, and so I wanted to finish with a few messages from my journey to you guys, since this is a very young audience. And you, as I said already, you are in a stage of the last year of PhD where you start to wonder what's going to happen. So the first message I have is don't rush it and work hard for it. So don't be too stressed. Just make your choices and see if they happen, because there is also something that you cannot control. So don't rush it. The second one, at least from my experience, choose the best people you can when you want to work with, you go to work with somebody else. Because if you stand on the shoulder of giants, you can do more. You put yourself in a better environment, a more challenging environment, and that's very important for your options in the future. And the last one, no panic. Uncertainties and failures, like paper rejections, interviews that do not go well, or other things, are part of the journey. So just take it easy in a way, and no panic, and everything will be, I think, okay at the end in a way or the other. And that's it. So I thank you all, and hope you enjoy it.
So Marco, thank you for this fantastic speech, very inspirational, we can say that. So now it's the time of the most formal part of the ceremony. So
I have a tie.
We can stand.
Ooh,
and so
beautiful.
This is for you. I want to remember that this is an award that comes from ESMEC, which is an EFMC accredited school in medicinal chemistry, and we believe that you deserve this.
Thank you very much.
Certo. Okay.
Okay. Well,
So,
thank you again.
Thanks again.
Good luck.
So, before closing, 2 tips from today that I would like you to remind. First, please consider yourself always part of the alumni community of ESMEC, okay? Please feel part of the community. because feeling part of a community is so important that I would add this as a tip to those already showed by Marco. And when you feel part of the community, maybe in 10 years, because there are precise requirements for this award, 12 years from the PhD. That's right. But please remember to apply, especially those of you who come from abroad. Please remember that you will be always part of the community for ourselves, and we truly invite you to apply to this award. And with this wish, I hope to see you maybe in 12 years on this part of the podium, okay? So thank you very much for joining. A posto. See you. Questo non gliel'abbiamo dato.
Sì, questo lo diamo a Marco. Anche questo è il...